Good morning, everyone. Welcome to our physical chemistry lecture. We are still in the second chapter of this course. And before we jump into things, just wanted to ask if there are any questions. I remember at the end of last week's course, there was a question which wasn't really clear to me, but you can still write it in the chat or ask the assistant. Unless this pops up now, I proceed. We are in the second chapter of this course, right? In theorems and postulates, and we discussed first a little technical introduction on Bra and Ket notation and expectation values and eigenvalues. Then we introduced the emission operators, the series expansion, eigenfunctions, and we are currently in parity. In particular, we noted down our theorem number 6. We're based on the fact that things commute with the Hamiltonian, right? If your potential is even, right, then the solutions to Schrödinger equation have to be of definite parity, right? So if V, the potential, is even, there is definite parity for all the solutions of Schrödinger's equation, okay? So definite parity means that they will be either odd or even, okay? Now, this is the reason for the nodal structures you can observe in many cases strictly, and also approximately. If your potential is approximately even, right, you can break that symmetry, of course, but you can in many cases think of it as approximately to some first order. It's an even potential. So approximately, you should recover the kind of nodal structures you're familiar with for the quantum harmonic oscillator or the particle in the box and so on. So this is what we mean by definite parity, that the function is either odd or even, and we saw this for something like the quantum harmonic oscillator, right? So we discussed this already. Now I'd like to, so let's put this for example again. Consider nodal structure in solutions for particle in the box, quantum harmonic oscillator, H atom, right? These are all strictly even potentials. Now, there is another aspect where this is important, right? It's not only about how things look like, but there's also practical importance. Of practical importance. Right? And this is when you calculate integrals. So for the calculation of integrals, if you calculate an integral of an odd of the product of an odd and an even function, it will cancel out. Okay. So for any psi of x odd times phi even of x, right? This must be 0. Okay. Now, that might seem a little bit abstract, so let me give you a specific example of this, where this can be exploited, and it's an example I like very much because it comes from the research in my group. So let me just briefly explain this to you. We discussed specific example. We discussed the Hellmann-Feynman theorem in the beginning of the course as an example of the Hermitian operator. And so you know that the derivative of the energy with respect to lambda is the expectation value of the Hamiltonian with respect to lambda. Now, suppose that lambda interpolates your nuclear charge Z. Suppose there's a nuclear charge Z as a function of lambda. So suppose then you can have an initial nuclear charge, and we simply interpolate this linearly for lambda going from some final initial charge to some initial charge. And in this case, 0 smaller equals lambda smaller equals 1. Right? So for any value of lambda, you have an interpolated nuclear charge here. And if lambda equals 0, you have the initial nuclear charge. And if lambda is equals 1, you have your final initial charge. Now, we can do this in a continuous fashion because we are only doing this in theory, right? So you should know from thermodynamics that sometimes you can couple state functions which are not physical in order to calculate physical or real observables. An example in thermodynamics is that you go to calculate your entropy changes by changing your system into the ideal gas law, and then you calculate there the actual change, and then you interpolate it back again into your final state. And so this is also called a thermodynamic cycle, right? So very common in physical chemistry. As thermodynamic cycles. So the law of Hess for enthalpy exploits this, right? And it's really related to the first law of thermodynamics, the conservation of energy. And you have to think about it like this: if you have some four states, right? And you're interested in the energy difference between the states illustrated as square and triangle. Now, that energy difference might be hard to calculate or hard to measure, right? Now, this is, but they correspond to reality. So you're interested in this difference, let's say, in thermodynamic properties such as the entropy. Then you can transform this mathematically in a model which is non-real, right? So this would be the real system. This would be the unreal system, right? Now, this is difficult to obtain for whatever reason. And then it could be easy to obtain the delta as unreal. Okay, then let me put a prime here. And that could be easy then. And then you transform it back again to the difficult and to the real system, the triangle, right? And now because because we have a conservation principle, right? The path doesn't matter, and so you can sum up these three arrows, and in the sum over the whole cycle must be zero, right? So if we don't know the difficult real thing, we can obtain this by going over non-realistic, easy states, states that are easy to be described. So this is very common, and so for this reason, it is very interesting to consider non-integer nuclear charges as well, right? So then you can ask questions such as, how does the change in chemical composition affect my chemical properties? Now, you can, of course, remove the atom and then plug in another element to observe this change, or you simply interpolate the nuclear charges. No? Either of those two can be easier to do. It depends a little bit on the context. Anyhow, so let's suppose this is our Z. Then the Hellman-Feynman derivative, you can write this, of course, as a chain rule, right? And the Z we defined up there, so this is the same as dZe times delta Z, right? So it's this difference here is delta Z, right? If you differentiate that linear function and lambda, you just inherit this delta Z. So the question is, what is this derivative here? Okay. So we can use the Hellman-Feynman theorem for this. So dZe is the derivative of dH dC phi, right? Now, if you differentiate the Hamiltonian with respect to Z, the nuclear charges, as discussed in the first couple of lectures, the nuclear charges only show up in the external potential. So this is really phi. And if you differentiate the external potential with respect to nuclear charge, you're just inheriting this distance-dependent denominator. And that is for any nucleus I in your molecule, okay? And at its position I. Now these are, of course, vectors. Yeah. So what is this integral? Well, 1 over r is just 1 over r around the nucleus, right? It's a multiplicative potential. So this is simply your electron density, so your phi squared, right? times 1 over R. Yeah. So this is your rho. Now, imagine that you consider the H2 molecule. The electron density rho, and this is my x along the molecular axis. My rho would look something like this, right? And this is where your nuclei is C, right? The 2 nuclei. C equals 1. That's your first nucleus, and that's your second nucleus. Okay. It should have exact same height. And that is in the space, this is the position R2 and R1, okay? Now, this is how the electron density looks like. So this integral, the R rho R minus Ri. And I get this, if I use this to estimate what the derivative would be with respect to changing, let's say we change H2 to helium, okay? Both systems have 2 electrons, so no change in electron number, just your electron density has to change, of course. And we also suppose we transform our first atom, right? So our first atom goes from hydrogen, and then helium has twice the nuclear charge. So this is helium. Z2 has now 2 protons, and Z1 is 0, right? Went down to 0. So this is where it used to be. And now all my electrons are on my helium atom, right? Okay. So suppose we want to evaluate the derivative of changing the energy of the H2 molecule into the helium atom. So we want to evaluate the lambda of the energy at the system being H2, okay? And so then we have 2 terms like this. There's the dr rho times delta z equals 1, right? R minus R. And now at 1, I'm going down with my nuclear charge. So for the atom 1, this should be just -1, right? And then we have the derivative for the other atom, which is +1, okay? Now we can collapse these 2 integrals. Then we have dr rho, and we have, we have once the 1 over R minus R1 minus, R2 minus 1 over minus R1. So we have 2 times 1 over R of opposite sign and at the 2 positions. So let me try to draw this in here. I change the color for for this term, okay? This is a kind of a potential, right? Let's call it V. And so my potential is negative at R1, so it looks something like this, right? And here the same, but then it also has to become the positive potential for R2, right? So it must look something like this, right? Okay, so now maybe you see this already. This is an odd function, right? And this is, sorry. And, this is an even function. Make this white again. All right, and you can imagine now if I integrate all of this, right? The product of all of this up to here, it has one sign on the right hand side. So I integrate this times the white function, and on the left hand side, I integrate the positive part times the red function. And you see these two integrals, left and right, they must be the same. So this means that this entire derivative must be zero, right? So this is just an example, right? It basically means for any, so this must be true for any homolytic diatomic, right? Must be true for any homolytic diatomic. For example, if we take N2, right, the most abundant molecule in air, and we change it to 14. What's 14? Silicon, right? So imagine you have N2, same picture for N2 to silicon, right? Only here your two nuclei have nuclear charge equals 7. So this would be nitrogen, and then when it's 14, you have silicon, the electron density is symmetric. Your first order derivative must be 0, right? So you didn't have to calculate the electron density to know that, right? So knowing something very basic about the nodal structure in your Hermann-Feynman derivative allowed you to figure this one out without a single numerical calculation. And this is the reason why these nodal structures are so important and extremely useful.
Sorry, I just want to ask how you drew that odd function from, yeah, I think I missed that part, how you drew that.
So this odd function, the red one, right, is this V. I'm sorry. Thank you for asking this, right? It's this one, right? So you have a 1 over R on the R2 position. That's this one here, right? It's just 1 over R. And then on the R minus position, you also have 1 over R, but it must be of opposite sign, right? In this bracket, because one nucleus goes down and one goes up, right? And so that's why you have this change of sign here. Do you see it now?
Oh, yes, thank you.
All right, thank you for clarifying. Yes, but you see, this is the important point is you have this structure, right? You have something even, the electron density, times something odd, this funny potential, right? This derivative of the potential, right? So this is a very common sort of integral you might be looking at, right? And apart from the symmetry of these two functions, you don't need to know anything to determine that the integral must be 0. All right. Now I'd like to go to the next subchapter, which is also very fundamental and very important. Okay. So this is the chapter 1, 2, 3, 4, 5, 6, 7, 8, and I'd like to go now to chapter number 6, which is measurements and superposition. Now this is related, you really have to know this because it's maybe less important for your daily life in the lab, but it is very important to interpret what you're doing in your daily life in the lab in terms of proper quantum mechanics. So to properly understand what's happening, right? Properly meaning in ways that are consistent with the picture of quantum mechanics. Right? You really have to try to get behind this subchapter. It's also important in terms of outreach, right? If you talk to non-chemists, right, to the layman, you have to have some sort of notion how you explain, I don't know, Schrödinger's cat, right? Or people who claim that you can tunnel through walls because of quantum mechanics, right? Why is this a ridiculous notion? You have to be able to say that, right? And so this subchapter should allow you to do that. Let's remember that psi is our state function, okay? So due to the particle and the double slit experiment, right, we know that your particle can be described by this function, right? But when you measure things, right, you need to detect something somewhere, right? You have a detector somewhere. And so remember that experiment, right? The electron emitter, emission, it shoots out electrons, and you can detect them, right? These are simple, very simple technical machines you can use for that. So the emission, you have to heat some metal or apply some voltage, and then you detect this, right? And you will detect each electron, right? It's like a particle, right? And then you go and you say, okay, now instead I shoot this at the wall like this, and I detect afterwards, right? And then you get this detection pattern, right? Where you on your detection screen, it looks like a superposition of a wave, right? So the particles, they don't know. Each time you detect one, once it's here, once it's here, once it's there, right? And then multiple times there, many times here, very rarely here, many times here, right? That's how you get this frequency plot, right? So you're just counting how many times you detect it. And so from this simple experiment, right, you must remember that there's something probabilistic about it, and that you don't only measure once, right, but you measure many times, right? And then when you do that, you get an average. That's your expectation wave, right? But the single experiment, right, that gives you just one number. That's the eigenvalue, right? That's what the single experiment measures, right? And so this subchapter is about that, right? How can we formalize this? Okay. So what quantum mechanics was designed to do, right, by construction, right? This experiment came first, the double slit experiment. This was first, and people wondered, how do we describe this? Clearly, Newtonian dynamics or any classical mechanics would not be able to explain this kind of wave-like behavior, right? But from the wave mechanics from fluid dynamics would do, right? But then there are funny things, right? Because sometimes it's still a particle. It's not really a wave of a fluid, right? So when you emit, right, or when you detect here, it makes cock just once, right? So we have this duality, right? Which you should have already heard about in high school, right? So now is the moment where we should formalize this a little bit better. And so in quantum mechanics is really, if you wish, you could view it as a way to account for probabilities, right? So we want to deal with the probabilities of possible measurements or measured values. Let's put it like this. Okay. So the possible outcome of Schrödinger's cat, right? One possible outcome is that the cat is dead, and one is that it's alive, right? So it's as if you shoot the electron before the screen, before the electron here hits the screen, you know an electron is coming, but you don't know where it will end, okay? Not that particular one, right? If you do it many times, you know how they will distribute. This is very solid. But any single one, we do not know where it will go. And that's the picture of the cat. You will not know if the cat will be dead or alive. So so it's about this probability of being either dead or alive. And so here's the example. Right. Probability P to find particle. Now it's formulated in general, right? In chemistry, the only particles we care about are electrons. So replace in your mind, you can replace safely particle by electrons, but to keep it general, we are talking about particles. So the probability P to find particle at time t between x, so somewhere in space, right, and x plus dx, right? So within time t, at time t, you have this window in space where you look, is my particle here, right? And this probability is given by dx. So the smaller the spatial window you're looking at, the less probable, right? So this must enter here, times your wave function squared. Okay. So this is your state function, right? Is basically supposed to be the square root of this probability, right? And this is also known as Born's rule. So Born is one of the founding figures of quantum mechanics, and in particular in the interpretation of quantum mechanics in terms of measurements and superpositions, right? So this is the probability of finding your particle, right? So where are the electrons, right? And so what you're measuring here, right? This distribution is basically proportional to psi square, and this is the x, right? We're integrating over time, right? This will converge towards something, right? So this is a very practical thing, right? It's not abstract, okay? This is how in the beginning people actually measured such distributions, right? And of course you measure only the square, so then you have to wonder what is the square root? And that gets you to imaginary numbers, of course, and so that's why we have that and why we have to take this into account, right? Okay, so the interesting thing now, and you should know this, that the wave function squared is your probability, right? So Born's rule should be something you should have heard about it. We want to generalize this now, right? What is the probability for all possible sort of results from measuring some property B, right? So what is P for all possible outcomes of measuring property B. Now, this question implies that you already have an idea of how to measure B in terms of quantum mechanics, and that means you need an operator, right? You need an operator. You need the eigenfunctions, right? You have to solve that eigenvalue problem. So everything we discussed about already, right? All the theorems, they form the basis for actually being able to understand this question, right? Even though the question, of course, is quite succinct and looks easy. So let's suppose our variable, right? So we had x and we have t, and we have the spin variable and so on. So let's suppose, let's replace all of that. We could replace it by tau, as we did already, but let's, in this case, let's just use q. So q refers to all 3n coordinates and spin states in an particle system. Okay, and then we can write that this is our problem. The operator of our property B, a hero, is operating on some eigenfunction, let's call it G, of our Q variable, right? So all our variables were wrapped into Q. This thing must be an eigenvalue equation, right? And that's really thanks to Schrödinger, who said, well, if you look at these patterns up here, right, it looks like a wave. So let's use wave mechanics. So let's have eigenfunctions, right? So these are differential equations, just like in wave mechanics, right? All right. So that's the ansatz, right? So you know that already. But what we care about now is that we want to see how any single of these solutions, right? How can we recover that pattern behind the double slit? Right? How can we represent that? How can we relate that to whatever you actually measure in your experiment? Now this is a hero, and so this means the set of eigenfunctions is complete, right? As we said before, and so we can expand, right? Our state function, we can expand it in this. So we write psi and then q, and our time, we want q and time, is the sum over these eigenfunctions in q, and we make the coefficients ci time dependent. Okay, so at every you keep, imagine you keep time still, you make one measurement, right? It's this one measurement at this point in time, you will get a linear combination in your eigenfunctions, g of q, and then at the next moment in time, you will get a new linear combination. So these are time-dependent coefficients. Right. So it's a very simple ansatz. You basically consider time to be separable, right? Now that's a little bit of violation with respect to relativity, where Einstein exactly pointed out time and space is related, is not independent, right? But this is our ansatz, if you wish, right? And at the microscopic level, usually the relativistic effects are negligible for such light particles as so where gravitation plays very little role, right? That means when your masses are low, then this is probably a good assumption, right? All right, so this is our state function then. All right. So far, nothing really new except that we folded in the time, but quite straightforward. And now, how do we get to this probability business, right? And this is actually quite technical and easy. Just assume that we want to normalize things, right? Now, why would we want to normalize things? So that we can compare them. Let's say your buddy in Australia does the same measurement, and things are a little bit different, so you normalize, okay? So you're comparing really apples to apples. And so when we do that, we are saying 1 must be equals the integral d tau psi psi, right? Now we plug in our psi. And now we use the index I for the complex conjugate. So let's use K for the real part. And we can factor this out. All right. Now we can write these sums to the left of the integral, so the order of integration doesn't matter, and the coefficients do not depend on our tau, right? So the tau is related to our q, right? Sorry, I'm going back and forth here, but so tau or q. So we have our Ci, Ck, complex conjugate, d tau, Gi, Gk. Well, and we had the theorem that the eigenfunctions are orthogonal, right? So this must be delta Ik, right? I think it was theorem 2. Now that means whenever I not equals k, it's 0, right? And as an effect, an entire summation here of I and k, one symbol dies, right? Only your diagonal elements survive when I equals k, right? So this thing, and if I equals k, then your integral is just 1. So what this means is that you just have the sum over Ci, okay? I could have taken k just as well, it doesn't matter. It's just a different index. And that's, of course, simply the square, right? And that whole thing must be 1. Now, when you look at a sum of squared things being 1, that's very reminiscent of probabilities, right? When your probabilities go up to, when you sum them up, you should get 1 in total, right? Something must happen, right? So all your possible, let's say, reaction channels have to add up to 1 in total, right? So this is very reminiscent of probability. I see a question here in the chat. I believe this refers still to the example with the nodal structure. I'll answer that later if that's okay. So this is now basically the reason why we are talking about probabilities here, right? The point is, right, when you work until now, right, we didn't really touch probabilities, right? And so it's now that we see there is something that looks like a probability, and so we might just as well call it like that. All right, it's 11 o'clock. Let's take a little break until 11:15, and then we continue with the expectation value, which is the next natural thing to ask once you have probabilities. So we define the problem, right, through the eigenvalue equation, and the corresponding expectation value then should be the expectation value for our operator B. And now we can insert our series expansion. This is just a notation. And now we substitute. And that means we have our double sum again, IK CI complex conjugate K integral, and now GI B GK. Okay. Now, as B is being applied to GK, of course, we get the eigenvalue in front of it. So this here is B K GK, and hence we have I K CI CK BK d tau GI GK. And the remaining integral, of course, we know it's our Kronecker delta, which kills one of the summation symbols. And so what survives is your sum over I CI squared BI. Okay. Now, we said that this is a probability. So what this looks like, right, awfully much, is exactly what a probabilistic expectation value would express. So this is the same as the probability of I times the outcome of I, right? So this is our probability. Well, I've written it up here. The probability to measure the ith eigenvalue of B, that is Bi. Okay. Now, this is for any operator, right? For every measurement, any measurement, you can express it like this, right? So it's very general. It's reminiscent. So compare this to statistical thermodynamics. For example, good old Boltzmann telling you that the average energy equals the sum over all your states, the energy of that state, times its probability, which is e to the minus beta ej over some normalization constant. Right? And that is nothing else than the probability of state J. So you know that in thermodynamics, the higher your energy, exponentially the probability of that state to be occupied decays, and thereby you get the population patterns, population distributions in statistical thermodynamics, which then relate to the macroscopic observables you would measure in the lab. And so this is the very same expression, right? Only that now our probabilities are slightly different. They are no longer these Boltzmann factors, okay? But the structure, right? Sum over probability times times value, that structure is the same. And so you have something quite beautiful emerging here, right? You get at the electronic level, you get this probabilistic expressions, these expectation values, and then at the atomistic level, you get them again, right? And so this is, if you wish, that there is some intrinsic beauty and repeatedness of mathematical formality, which many people would consider very elegant and beautiful in itself. Are there any questions up to now? Okay, that doesn't seem to be the case. Then let's continue. What happens if you have degenerate levels? So what about degeneracy? Well, that's quite easy. You write your B clearly as a sum of terms. Right? So this means you have some Ci squared Bi plus Cj squared Bj plus Ck squared Bk and so on. Right? Now, if you had a threefold degeneracy, it would mean the eigenvalues are the same. So you would have your coefficients are not the same, but the eigenvalue happens to be the same, right? So I can write just one of them here, right? That would be for threefold degeneracy. And that, of course, means you can factor this out, right? So this thing then becomes Bi times sum over L equals 1 until 3. So let's put it put directly in N here. CL squared, right? For n-fold degeneracy. Okay. So basically, your sum has multiple terms with the same eigenvalue, so you can factor it out and then collapse that that probability here. This is then your P degenerate, right? Pn tot or whatever. You can collapse that in one bulk if you wish. What's the probability of just measuring that degenerate eigenvalue is the sum of the probabilities of each of those levels, right? Okay, so the interpretation now is that psi, right, as a sum over these coefficients, right? So it's like it corresponds to a superposition of eigenfunctions. And these are like state functions, right? So these are the superposition of state functions of which belong to some operator, right? Belonging to. So let me put this up here. Property B, you measure as the expectation value of operator B, right? So this is the eigenfunctions belonging to your property. Your property has some state functions, right? These eigenfunctions, and you have to superimpose them, and each one gets weighted by the coefficient, which as you square that coefficient, it gives you the probability of measuring the eigenvalue of that function, right? So you're seeing, I hope you see this kind of picture, right? So you have some property, it gives you a bunch of functions, right? G1, G2, G3. And if you want to make it just one measurement, right? Of course, you can get an average, but just one measurement would get you just the corresponding eigenvalue, which is attached to it. And if you stand there and measure long enough, on average, you will obtain the probability weighted values of these eigenvalues. So there is this coefficient which tells you something about how important each of these functions is, right? Well, some functions might be more important than others, right, for that particular property, right? And so that's what this coefficient tells you. Okay. Now, if these coefficients are so important, how do we find them? And now again, we are basing the answer on what we already covered. Right? It's the projection trick from theorem 3. So we use psi again, sum I, ci, gi, and then we multiply from the left with gj. And so gj psi becomes d tau gj psi, and that is nothing else than, thanks to your series expansion, right? That's nothing else. So putting this together, then ci d tau gj gi, which again is our Kronecker delta. So we have some ci delta ij, and so only cj survives. Right? So if you want to know your coefficient ci, you project it out using the basis function of I, right, of the ith state. You can call this Cj, I just turn this around. So Cj is my projected coefficient, also known as probability amplitude. Of my state J. So if I know my eigenfunctions, I can, and I have my expansion, I can always project out the corresponding eigenvalue. Right? Now, so this means my Pj equals Cj squared equals Gj psi squared. Now, what you have here is the overlap integral of two functions. Right. So the more the eigenstate J overlaps with the entire wave function, right, the bigger is the contribution of that eigenfunction J to the entire function. I mean, that's pretty obvious, but that's now explicitly written down here for that probability amplitude. So if this is unequals, if this is non-zero, then this means Gj somewhat, yeah, other components, of course, but somewhat resembles your total function, right? So in other words, there is overlap. If it's zero, right, then there are two possibilities. Either Gj is 0. So let me, Gj at your variable q is 0, and at the same time your total state function at q is non-zero, right? So that's a region where your electrons are, but the state, the eigenfunction J does not contribute here, so it's 0, right? And 0 times something, your integrate is 0 overlap on integral. Or you can, of course, have the eigenfunction somewhere goes around in space, because mathematically you want that. So it's non-zero, but your system is not there at all. Right? So those could be possible reasons. In any case, there's no overlap. Right? So just because the overlap integral is 0, it doesn't mean the function is 0, right? So you have to be careful with this, right? Two non-zero functions can still have a 0 overlap integral. So if you think about this twice, it should be obvious by then. Okay. I'd like to give you an example now, because this is fairly abstract, and we want to see something more specific here. So let me give you as an example the particle in the box. You should be familiar with this, right? And we will consider the measurement of the energy, okay? Energy measurements. So we're not going to solve it. You did this already, right? So I presume this will be known to you, and you can look it up again, of course, if the solution is correct. But that's not what we want to do now. We want to take the solutions of the particle in the box and submit them to the probabilistic treatment as we just discussed it. Okay, so known is the solution, right? Psi of x, and in this case we have this normalization constant. It's the square root of 30 x times L minus x for all 0 smaller equals x smaller equals L. Okay. So this is the total wave function, and we now also know the eigenfunctions of the eigenfunctions of this Hamiltonian. Gn equals 2 over L sinus n times pi times x over L. Okay. And now we're gonna expand our state function in this bunch of eigenfunctions. Okay. So we know the actual true wave function, and we also know the eigenfunctions. And the typical picture, which you should know by heart, is some box. This is the potential. This is x. This x equals 0, x equals L. And at 0, your potential tends towards infinity, and also at L. And so in between, your potential is 0. Okay. 0 here. All right. So this then means that your wave function is this sinusoidal behavior. And you also know that as you go up in the particle in the box, very important, the distances between the levels increase quadratically, right? So this is some 0, some 1, some 2, and so on. All right, this is the eigenfunction, right? G3 then, G2, and so on. But the total wave function is known as this one, right? That's the top. It's the total function, and that's just one of the eigenfunctions, so they make up the set of eigenfunctions. Okay. All right. N, of course, can go up to infinity, and so we expand psi equals sum n equals 1 to infinity Cn Gn. Okay. We can now get the coefficient, right? So we project and your coefficient Cn, as we said above, is the Gn eigenfunction projected onto psi. And in our case, our tau is just x, so we go from 0 to L, and then we plug in our Gn, the complex conjugate. It's just a real function, there's no imaginary part, so that's not needed in this case, and we can just write this out as 2 over L 1/2, and that's our square root. I'll write it like this in the denominator, because then we can also unite it with the L to the power of 5/2 for the wave function, and then we are left with dx. So these were the prefactors. We have the eigenfunction, and we have our wave function. Okay. Now this prefactor, simply 60 square root divided by L to the 6/2, which is L to the 3. Okay. And this integral, you can look this up in integral tables. It's tabulated, right? We don't expect you to actually do the math for deriving such integrals. It's quite complicated if you have to derive this from scratch. It takes too much time, and it was done already many times. So we typically just look them up in the tables, and it turns out that you get the integration limit here, the L to the 3 in front, and n to the 3, pi to the 3 times 1 minus 1 to the power of n, bracket closed. And now you see, of course, immediately this thing cancels, and 2 is the square root of 4. So 60 times 4 is 240. We keep the square root over n to the 3, pi to the 3, 1 minus 1, n. So this is your coefficient Cn, and then the probability, of course, we square the whole thing, we get the probability of n as Cn squared equals 240 n times pi to the 6 1 minus 1 n power of 2. Okay, so this is the probability to observe with a single measurement, right? Suppose you can measure this, let's say that spectroscopically, right? You measure this particle in the box, the energy, with a certain probability, right? Now, what is the most probable state? Right? Now, by intuition, you should answer to this the one that is energetically the lowest. So this is probability to measure eigenvalue. Now, what is the eigenvalue in the particle in the box? It's An equals the energy, let's call it En. En is h square 8mL square n square, which is your level, right? So the energy grows exponentially, quadratically with the level, right? But your probability decreases with the level, right? And so we can easily show that, right? So let's put the level here, n, then we put the eigenvalue, En, and we put it in units of the prefactor, right? So we don't have to care about that. Right? And then we put our probability. Okay, let's do this. So this column is easy. 1, 2, 3. How far do we want to go? 5. Well, let's see. So let's go for the first energy. Okay. So we plug this in, and if you put n equals 1, and you calculate this 240 over pi to the 6, what you get in terms of probability is 0.998550. Okay. What happens for 2? Right? Your energy grows quadratically. So here we have 4. Now, if you put this in 2, right, you see here, we will get a multiple of -1 for even exponents that will cancel exactly with the 1 in front of it. So this must be 0. Then we have 9. And for 9, we find a probability of 0.001, right? 370. A reduction of a factor of nearly 1,000. Okay. So that's your next probable event, right? 1,000 times less probable. The next possible event, energetic. Okay, 4 is again an even exponent for our probability, so we are at 0 again. Right? 5, 25 in our energy units, right? So 25 times more energetic. We have a reduction to 0.000. And then 0.64, right? again, 2 more digits, zeros, dramatic reduction. For 6, 36 is 0 again, and 7, 49, at 0.00000. Again, we lost 2 digits. In this precision, right, where we have 6 digits after the point, the probability is 0, numerically 0. Okay. So we can illustrate this on a graphic where we put the probability and we put the levels, right? 1, 2, 3, 4, 5, 6, 7. At 2, we must be 0. At 4, at 6, right? And then, so this decays so rapidly, we should probably put something like the log p, okay? So let's start here at 1, 0.1, 0.01, 0.001, 0.0001, and then it gets too small. So at 1, we are nearly at the nearly at 1 here, right? And then we must go down to 0. And then at 3, we had 0.0013. Right? So that's roughly here. We go up here. Right? And then we must go down to 4. And then at 5, we are already, yeah, on this scale, it's very, we are hardly anywhere. And then, and now for 7, we are numerically, we cannot see it. Right? So this is, right, if you wish, if we draw a line like this to our non-zero values, this is an exponential so there is this physicist called Al Bartlett. So this keeps on getting worse and worse, of course, as you imagine. Now, Al Bartlett, you can look him up on YouTube. He has an entertaining lecture on the exponential function. He was a physics professor. I think at the University of Boulder, Colorado. He made the statement that the biggest problem with human mankind is this continuous underestimation of the exponential function. So this is the exponential function is continuously underestimated. Right. So you can imagine now, if somebody wants to tunnel through a wall, right? You would need fairly high energies to do this, right? And the probability for this to happen, right? You see how quickly it decays for just the first couple of accessible levels, right? And so it's really while mathematically it's maybe non-zero, the probability that you can tunnel through a wall or some macroscopic object, in terms of quantum mechanics, the probability when you evaluate it is most certainly negligible. Now, what's happening here, right? There are probabilities that are zero. Why are they zero? They overlap G, N, even, if your n is even, with psi must be 0, right? Now, you know, we just discussed this with the parity, right? So if you look at those solutions, right? So this is G2, right? This is G4, right? These functions are odd, right? Psi, if you scroll up, psi has x squared in there, right? Odd function, sorry. Psi must be an even function. There's an odd function. Your overlap integral must be 0, right? Due to symmetry. We didn't have to calculate those elements, right? Just by looking at the solution of your eigenfunctions and the psi I gave you, you can infer that all probabilities for your even quantum numbers to be measured, all these probabilities are 0. You will never measure them. All right, I'd like to close this chapter now. There was a nice question still. I'd like to answer this question now. We finished this subchapter 6, and we will discuss tomorrow the eigenfunctions of the position. So the question was very nice. I mentioned the derivative going from H2 to helium, right? So so this is where it used to be. Now you can imagine going the other way. Right? Let's suppose you're growing the other nucleus to helium. Right? And then what's the difference, right? This was our R1, R2, R1, R2. It would basically mean in one case the helium is shifted to one position and in the other case to the other position. But the energy should be the same. So you can see the energy of helium is below the energy of H2, right? So energy-wise, this means we go down here and we go down here, right? So this is our energy. This is your helium on R1. This is your helium at R2. Of course, the energy of helium does not depend on its position in space, so that must be degenerate, right? And this is the energy of H2. And based on the simple symmetry argument, you also must see, oh my God, there's actually a maximum, so the gradient must be 0. Now the same holds for ozone, right? If you define a path for ozone, let's put an oxygen here, another one here, another one here. Of course, things depend on geometry, but consider the linear geometry. Then you have some electron density here. Your central oxygen has a slightly different one. But if these two guys are on the same distance, right, and it's linear, the electron density on the left and the right-hand side must be the same, right? And so then if you come with a perturbing potential, let me show again this, which once depletes some protons here, and here it grows some proton. So you're going now from oxygen, let's say, to nitrogen on this side. And on this side, you would go, what is this, fluorine, right? So that would be a new molecule. Then you see the derivative evaluated at O3 must also be 0, because the would also be an integral of the red curve multiplied with the white one. So this is an odd times an even function. But of course, it hinges on these electron densities here being exactly symmetrical, and on the potential being of opposite, exactly symmetrical, except for the opposite sign. If that is the case, the integral of the product of these guys should exactly cancel. All right, I hope that answered the question. I thank you for your attention, and I look forward to talking to you tomorrow. Unfortunately, I won't be seeing you. But anyhow, let me know if there are questions, or let the assistants know. Thank you so much.
Sorry, thank you.
Yes, please, go ahead.
I do have a question.
Yeah.
It was at the projection,
Yes.
where you defined CI as
Here or earlier? Earlier?
Yeah, can you just quickly explain again what you said there with the Gj, if that is 0, or if the wave function is not 0?
All right. Yeah, that's so suppose this is your wave function psi. Okay. And now I come with my eigenfunction G. Right? Let me change this to different colors. So suppose G looks like this. Okay. Now at this location of Q, right, you would have this situation, right? Here, your G of Q is non-zero, but your psi is 0. Mm-hmm. And then if you go to this location, right, here your G is 0, but your psi is non-zero. And so if you now build the product of these two functions, right, the product psi times G would be flat everywhere, because either the red one is 0 or the white one is 0, right?
Yeah.
And that shows up. That means that your Cj will be 0. Right? So that's this case here, right? So your Cj can either be non-zero, or it's 0 for either of these two reasons.
I think my question was more on the definition of Cj itself. It's just the eigenfunction projected on the wave function of the particle.
That's right. So we do the projection trick from our third theorem up here, right? Which means we multiply with from the left, we multiply in the eigenfunction and we integrate, right? Mm-hmm. So that gives us this expression here, right? Mm-hmm. And now you insert your series expansion, then you come here. And now due to the orthogonality, that was theorem 2. We only one term survives, right? The sum in front cancels and only the J survives.
Yeah, I think I'm struggling with the meaning behind this projection. I think that's more the problem here.
So the meaning is really this, when you square this, right? When you square this, then you get the probability. So it's the square root of the probability of J, right? So, and it is related then to this overlap, right? So that's, if you just think about this integral, right? You have the eigenfunction of one state, right? That could be one possible outcome. The eigenfunction of that outcome, it has an overlap with your total wave function, right? The whole thing. Right? And so the degree to which that matters is measured in your probability of J.
Oh, I see.
Maybe make some drawings, yeah, to see if it makes sense to you. You can, yeah, I would recommend to work a little bit with pen and paper, erase and then try out. But, yeah. You could also, you know, you imagine your psi here. You could draw multiple of these guys, right? And all sorts of colors, right? So all these colored eigenfunctions, they sum up to the total psi, right? And then you can extract the, so this total psi, right? It is expressed in these eigenfunctions, right? It's the sum over these colored guys. And now you wonder how important is any given one of those, right? And that's what this coefficient measures. And that is related to the probability of you measuring something, right? So from the total function here, let me go back to this example. I'm very thankful you're asking these things. So you see, this is, here we know the true wave function. So it's a privileged situation. Now this is something quadratic in X, okay? And now you also know these eigenfunctions. It's all these sinusoidal functions. Now which one resembles most X squared? Right? It's going to be the first one, right? So let's, so if you think about your first sinusoidal function like this, of course, so you can just flip the sign, right? Then this would be just half a sinus. And then you compare this to your quadratic true psi, right? So this is your G1, okay? The first state, right? And so then you can see immediately if I ask you, okay, this is the G1 and this is the G2, okay? Now, is G1 more important to describe psi than G2? You would immediately say yes, right? You can get more of it. Actually, G2 doesn't matter at all. There's no overlap because of symmetry. So let's go to G3, right? Then you have something like this, right? And so let's superimpose this, right? Here you already have G1, and now we put something like this, but the coefficient for this one will be much smaller, right? So your C3 is going to be much smaller than your C1.
Thank you very much.
No problem. All right. See you tomorrow. Bye-bye.
Bye.
Goodbye.